So welcome to the lecture on multi-degree of freedom system. So in this lecture we will discuss the stiffness influence coefficients. So we discussed in the previous lecture the flexibility influence coefficients, and we saw that if we know the flexibility influence coefficients, we can prepare the flexibility matrix, and by using that matrix we can write the equation of motion. Now we have similarly we have stiffness influence coefficients, because in equation of motion of a multi-degree of freedom system we have mx double dot plus kx equal to 0 for and multi-degree of freedom system undamped system. So we can write here mx double dot plus kx equal to 0. So here K is stiffness matrix and M is the mass matrix. So K is the stiffness matrix and the elements of the stiffness matrix are called the stiffness influence coefficients. So here K can be written as so we can see that the stiffness matrix that is made from stiffness coefficients influence coefficients, and it is n by n square matrix. So its elements k11 k12 and knn. So this we can find and we can make this matrix, and we can use directly in that equation. So we don't need to write the equation of motions and prepare this matrix. We can directly prepare the stiffness matrix. So here we concentrate on one element kij. So here kij, what is kij? So kij is defined as the force or moment required at any coordinate qi when a unit displacement, this displacement could be either rectilinear or angular, is applied at coordinate j, holding all other coordinates fixed, or all other degree of freedoms fixed. So here the stiffness influence coefficient Kij is defined as a force or moment. So it is force if it is the linear motion, and moment if it could be a angular motion. So what is the force that is required at a coordinate I when unit displacement is applied at j, while all other degree of freedoms have zero or fixed, so they have the zero movement. Similarly, kji can be defined as reverse, like kji is, we are measuring the force at j and we are giving a unit displacement at I. And again with this reciprocal theorem, this kji is kij. So therefore we will find these coefficients for certain example. So let's take one example here and we try to find out this. So we have this 2 degree of freedom system consisting of two masses m1 and m2 and two stiffness elements k1 and k2. Now we have to find the stiffness influence coefficients, and so the stiffness matrix K so it will have K11, K12, K21 and K22 because it is a 2 degree of freedom system. So this matrix will be square and 2 by 2 matrix, and we will have total 4 influence coefficients that we have to find out. So now as K11 or K12, K21, K22. So Kij, as we define that, we want to measure the force or that is developed as form of reaction when we apply a unit load at J. So here Kij, so the force at I when displacement unit displacement at j. So here now we give unit displacement here at so this is unit displacement. So we are giving unit displacement to the first mass in this direction, and we are keeping fixed all the other degree of freedoms must be fixed. So this mass is fixed, this is not moving. Now when we give unit displacement, we are going to measure the forces. So we are going to measure here the force, this, and here the force. So this is K11 because we are giving unit displacement at 1 and measuring the force at 1. Now we are giving unit displacement at 1 and measuring the force at 2. So this is K21. So now we will show the free body diagram for this system. So the free body diagram, so this is my first mass and this is the second mass. So now this first mass is having unit displacement. So when we are pulling, so of course here the force K11 is here. K11 is acting on this mass. When we give unit displacement, this spring will apply a force in this direction, opposite direction, that is K1 into displacement, and displacement is 1, so the total force is K1. Now we are compressing this spring, so this spring will apply a force K2 into displacement, so displacement is 1, so this force is K2. Now this mass, it is fixed, so the same there is no any, so here is a force K21 on this mass, and then there is a spring force that is K2 due to that spring, and this will be opposite to this direction. So now if we write the equilibrium equations for these two free body diagram, two masses, so we will have for this first one K11 minus K1 minus K2 equal to 0. So this implies K11 equal to K1 plus K2. So this is one stiffness influence coefficient that we have obtained. Now for the second mass, we have K21 plus K2 equal to 0, and this implies that K21 equal to minus K2. So we have got the second influence coefficients. So K11 is the force that is developed at 1 when we apply a unit displacement at 1, while in the K21 is the force that is developed at 2 when we apply a unit displacement at 1. Now for second other two elements, so we take the case when we have this mass system. Now we are giving in this case a unit displacement here. So this is unit displacement to the second mass. unit displacement and we are measuring the forces at both masses. So here the force will be k 2 because we are applying the displacement at 2 and measuring the force at 2, and here it will be k 1 2. We are applying the displacement at 2 and measuring the force at 1. Now we make the free body diagram. So the free body diagram here we will make for these two masses. So for this one we will have here K22. Now we are pulling this spring. So with unit displacement this will apply a force K2 into 1. So that is here, and this spring the same will apply the same force on this mass. Then K12 is another force that is working here on this mass, and this mass is fixed, so there will no be any stretching or compression of this spring K1, and therefore there will not be spring force by this spring on this mass. So we can write the equations here for equilibrium equations for these two masses. So here we will have K22 equal to K2, and from here we get K12 plus K2 equal to 0. This means K12 equal to minus K2. So we have obtained all the four influence stiffness influence coefficients, that is K11, that is K1 plus K2, K21 that is minus K2, K12 minus K2, and K22 equal to K2. So again from here we see that K21 equal to K12 equal to minus K2 due to the reciprocal theorem. Now we can write our stiffness matrix. So now we see that how we can find the stiffness influence coefficients for multi degree of freedom system, and how the reciprocal theorem, according to reciprocal theorem we can omit to calculate several terms, and we can easily complete this stiffness matrix. So this is what I discussed for the multi degree of freedom system that is undamped. So we only considered the mass and stiffness of the system, but we have also damped systems. So we have all the three elements, that is mass, stiffness, and damping elements. So as for undamped system, we wrote the equations for multi-degree of freedom system, and we find represented in terms of matrices. So it was mx double dot plus k x equal to 0. So this equation is for an undamped spring mass system, multi-degree of freedom system. Now if we have damping and we introduce the damping in the system, we have the C1, C2, C3 terms, then one more matrix will come into this equation, and we call it damping matrix. So we can write so this is equation of damped free vibration of a multi degree of freedom system. So we discussed the flexibility influence coefficients, we discussed the stiffness influence coefficients. Now we have the damping matrix, and therefore it has the damping influence coefficients. So the damping matrix C so the damping matrix C can be written as so this damping matrix C is also a square matrix of having n by n elements if it is a n degree of freedom system, and the elements of this matrix are called the influence the damping influence coefficients. So if we take this Cij, so Cij, it is defined as the force or moment required at coordinate I due to a unit velocity given at j coordinate j, while other degree of freedom have 0 velocity, they are at rest, so 0 velocity. So similar to the stiffness coefficients, we can also calculate the coefficients of this damping matrix, and so we can find the damping influence coefficients. So I thank you for attending this lecture and see you in the next lecture. Thank you.